Hey, this is Steve, E6WZ. Let's talk about mutual coupling. That is, what happens to a dipole or a vertical element when we put another element near it? Well, why do we care? Well, understanding this is the basis of any parasitic array. And by knowing the relationship between the parasitic tuning and the driver measurements, we can learn how to tune a parasitic array. Please try and stay with me on this video. This isn't just about theory, but I'm going to show how to practically tune any two-element parasitic array in the field for the desired front-to-back or gain parameter. I've been building Yagi's, Homebrew Yagis for about 30 years, and the traditional tuning method, which I've usually used, has involved isolating elements, sweeping them with the analyzer, and often doing field measurements to confirm the optimum tuning. It often involved multiple iterations of both parasitic and driver readjustment. This is unnecessary. There's a much simpler method where using an analyzer and sweeping just the driver, it can tell us everything we need to know about the parasitic tuning. And then we can dial in our parasitic array to match our model easily. First, let's do some experiments in the workshop here, in my messy workshop, on a small scale antenna I built on this little jig here. And we're going to learn about mutual coupling. Then I'll show some 4-neck-2 modeling, and we can see what the relationship is between that parasitic tuning and the front-to-back and maximum gain response of the array. Let's get started. All right, here's my setup. It's pretty simple. Got the little nano VNA connected to my laptop, and then through a piece of RG6 Coax, I'm connected to my jig here. I'm using a number 12 copper wire for the driven element. I don't know, I think it's about 42 inches long. Turns out to be resonant, half-wave resonant in and around 120 megahertz. I included a little copper plate here with an F connector, and this is my reference plane, and I did do an open short load calibration from here back to the nano in order to make sure our measurements are as accurate as possible. The jig is nothing more than just a piece of 1x4, screwed onto a wooden wine crate. I don't know, it's maybe about 4 feet off the ground. It's maybe not super accurate in the context of aberrant resonant wires and things in the surrounding area, but I think you'll see in a minute that's not really critical as much as the effect that we see when we introduce another element to this model. Okay, let's look at some measurements. All right, here's the nano VNA plot of that dipole. The chart I chose to show right now is the real resistance R and the reactance X. In fact, on the on the left scale is the real resistance, and the scale goes from 0 ohms to 200 ohms. And that's plotted in the green line. So you can see we're in and around 50 ohms, and then gradually increase resistance as we go higher in frequency. The sweep I chose was to go from 100 megahertz to about 140 megahertz. In the blue line is reactance, and the scale for the reactance is on the right side, and it goes from minus 100 to 100 ohms. Of course, zero reactance is in the middle, and the point where the line crosses 0 is when the dipole is resonant. So obviously this piece of wire is resonant, in and around 117 megahertz. Of course, below that resonance point, as we go lower in frequency, it becomes negative reactive. And of course, that means the antenna is too short. You'd need to add inductance to bring it to resonance. And above that, the wire is too long to be resonant. You'd need to introduce some capacitive reactance to bring it to resonance. Let's introduce a parasitic element now and see what happens. All right, I cut a piece of copper tubing, which is, it's maybe about 4 or 5 inches longer than my driven element made out of the number 12 copper wire. And I'm just sitting it on this board. I measured it out to be about 0.2 wavelengths away from this driven element, although that, the effect that has is another study altogether. But let's be clear, okay, nothing's been changed to this model. The dipole that we just measured is the same. Nothing's changed. Nothing is connected. All I've done is sat this piece of copper tubing here. Let's see what happens when we do a sweep now. All right, before we do our sweep, this NanoSaver program I use can use something called set as reference. So what I've done is this is the dipole sweep, and I've just set that as a reference so that it'll be preserved on the screen. So now I'm sweeping the array, let's call it that right now, with that other parasitic element added. And let's see what we get. The new sweep is the one shown in green, and the old dipole sweep that we did earlier is in yellow. So right away, you'll notice the real resistance from the dipole, which was 50 ohms, has now crashed down to, gosh, it's almost like, I don't know, maybe 5 or 6 ohms down here because of that element that we introduced. Higher in frequencies, the resistance curves tend to converge. I'm going to talk about this more in a minute, but this is simply because the piece of copper tubing we added is resonant in and around this frequency. What happened to the reactance? Well, you'll notice that the reactance has been lowered a little bit. We've moved and loaded down our dipole element, and the reactance is now somewhat lower in frequency. All right, let's add a different parasitic element. I've got one that's a bit shorter. Let's add that and see what happens. I just cut another piece of copper tubing, which is shorter than the one we just had on there. And so let's just replace that. So now we have a shorter element, parasitic element, in place of the long one. Let's do a sweep. Okay, as I had done before, I saved as a reference file that sweep we did with the longer parasitic element, and it's shown in the yellow curve. And I did a sweep just now of this new setup with the shorter parasitic element. And that sweep's shown in the green line for the real resistance. And what you see, of course, is that the dip in that real resistance has now moved up in frequency. Well, that's simply because that's representing the resonance frequency of that shorter piece of copper tubing. It's now up around 124 megahertz. But remember, nothing else has changed in this. The only thing we did was change the length of this copper tubing. Let's talk about what's going on. Let's do a quick recap of what we just saw. By the way, I just want to make it clear again that what we're measuring and what we want to measure in the field as we go further here is the real resistance. That is R, not impedance. Many analyzers will compute impedance and plot impedance, but that's not what we want to look at. Impedance actually is a sum of the real resistance and the reactance. So with just the dipole, we saw a typical response where the resistance gradually increases with frequency. As soon as we introduced the parasitic element, we saw a very pronounced dip in the real resistance compared to just the single dipole. That dip, as I'm going to explain, as I have mentioned, is entirely a function of the resonance point of the parasitic element. Well, and in fact, that's what we did. We included a shorter parasitic element, and indeed, the dip in frequency, the dip in the real R moved up in frequency. Okay, follow me along here. I'm going to use an analogy where, let's say with our dipole, because we're injecting current into the dipole, we're illuminating a light bulb. Well, as soon as we introduce the parasitic element, at the resonant point of the parasitic, we're going to induce or couple current into the parasitic. And therefore, I'm suggesting, the light bulb would be illuminated. It's not unlike, the parasitic is not unlike resonating a pitchfork, an audio pitchfork, when it's exposed to its tuned frequency. So if we follow that analogy along, at the resonant frequency of the parasitic, we now have both light bulbs illuminated. Well, that's like having two resistors in parallel. Basic Ohm's law, our resistance is going to drop. And that is only at the tuned, it's most prominent at the resonant frequency of the parasitic. Basically, the drive energy is being shared between both the driver and the parasitic. All right, let's just stay with that analogy and look at a frequency sweep. So at the resonant frequency of the parasitic element, we're going to induce the most current, and therefore we're sharing the current between the two elements, two resistors in parallel. We're going to drop the real resistance. When we're off of the frequency of resonance of the parasitic, we'll have less current induced and therefore less effect on the real resistance, either lower in frequency or higher in frequency. So to summarize, really, and it's important to understand that the parasitic induced current, is entirely and independent of the driver tuning, In other words, the dip in the real resistance is only a function of the parasitic tuning. It doesn't matter where the driver is resonant. All right, so what? Hey, let's look at some modeling now, and we're going to talk more about why this matters. For modeling, I use the freeware program 4NEC2. Let's build a model similar to the one we just tested. It's a wire about 45 inches long, fed in the middle in dipole configuration. It's about 4 feet off the ground. We're going to do a sweep with the wire and get a very similar looking profile as we had with the Nano. The sweep goes from 100 to 140 megahertz. On the left is the real resistance R, and on the right is the reactance X. So what do we get? A very similar, just linear upward trending resistance with frequency. The reactance showing a crossing at zero resonant point around 118 megahertz. The real resistance, in and around 60 ohms near resonance. Let's add a parasitic element, slightly shorter than the dipole, spaced about 0.2 wavelengths away. Same sweep, and we get something that looks real familiar. There's our dip in the real resistance shown in the blue curve, right around the parasitic resonance point. In fact, I overlaid them here too, and you can see that the real resistance has dropped from in and around 50, 60 ohms down to about 20 ohms at the resistance or at the resonant point of the parasitic. The light bulb is lighting up on that parasitic element. Well, let's have a look. In fact, Fornek 2 has the ability to plot current distribution on the wire. That's shown on the right here. The current distribution is the green line with its magnitude being represented by the distance from the actual wire representation shown in purple. So this run was done right at the point of maximum coupling, or the greatest dip in the real resistance. And you can see, in fact, that the current is quite high, in fact, almost equal to that of the driven element. And here's another sweep done at a lower frequency, well away from the dip in resistance, and you'll notice that the current distribution is less on the parasitic, as we would expect. Now, let's look at the relationship between this minimum R dip and the gain and front to back of this two-element antenna. A Fornek 2 provides output plots, just the same as the R and X plots we've been looking at, for both gain and front to back. In fact, here on the bottom is the front to back plot for this antenna. And you'll notice on the front to back plot, there's a swoop here that goes through 0 front to back. Well, this is, of course, when the antenna is acting like a reflector. And then below that, it's switching directions and acting like a director. The line that I've drawn here is the point at which, if you'll notice, the point of minimum dip in the R, or maximum coupling, between the two antennas, or the point where the current is almost the same in both the driven and parasitic element, happens to also be the point where the antenna appears to switch directions. In fact, if we do a zenith and azimuth far-field plot on that frequency of 112 megahertz, you'll notice that the pattern indeed does look almost bidirectional, both in the zenith and the azimuth plot. So here's the far field pattern, both the azimuth at the top and the zenith below. If we do a sweep at 115 megahertz, which you'll notice is above the point of minimum R dip. Well, obviously, in this case, we're acting like a reflector because the antenna is tuned above the frequency of the parasitic. The parasitic is acting like a reflector. If we tune below that point of minimum dip. In this case, the parasitic is tuned shorter than our operating frequency of 108 megahertz. The antenna switches direction and it's now acting like a director. And here are those two put together, tuned as a director on the top and tuned as a reflector at the bottom. So therefore, in summary, this dip in the real resistance will be our anchor point when we're working in the field to determine how we want to tune the antenna and where we want to tune the driver, either above or below that minimum dip, depending on whether we want a director or a reflector model. Let's talk about that. So in practice, we decide what center frequency we want our Yagi to ultimately be tuned at. And then on the tower, the analyzer is connected at the driver, and the parasitic element is then adjusted to bring the minimum R dip to the correct frequency to either tune the antenna as a director or a reflector model. So in this case, if we wanted the Yagi tuned where the vertical arrow is, it's clear that if we want to tune as a reflector model, for example, we need to shorten the parasitic to move that minimum R dip up, as shown here. So in this case, you can see that we've now brought the minimum R dip to a point where this antenna would now be tuned as a reflector model. One other thing, most analyzers can be calibrated at the end of a long coax feed, doing an open, short load calibration. And that can be really handy so that you could do your sweep from the ground or even in the shack. Okay, this is a key point. The next step is to match the coax feed to the driver at the frequency we've chosen. We can do this many ways. We can use an L network, a hairpin, perhaps a helical hairpin, a gamma match, whatever works. For example, in this case, you'll notice that if we're tuning the antenna here, we now have the parasitic at the right spot to act as a reflector. The reactance, we have to bring that up to have zero reactance at this point to have it at resonance, and then we would have to adjust for the resistive component to bring it to our 50 ohm match. The key here is this driver tuning or matching has nothing to do and is not in any way related to the pattern of the Yagi. That is to say, the gain or front to back. The gain and the front to back are only a function of the parasitic tuning. However, I'll point out that changing the parasitic, if you've got the antenna matched at this frequency, and you can change the parasitic, make it slightly longer or shorter, and you'll notice that we have a fairly steep curve here in the real resistance, and that will greatly and rapidly cause a mismatch because it's a fairly steep curve here with the resistance changing rapidly. So if the parasitic is changed in length, that's going to change your match, and you'll have to readjust the coax match at the feed point. I think I've said this before already, but I'm going to say it again. Remember, when you're using the analyzer in the field, we are looking for the dip in the real R. That is to say, the real R, which is usually plotted together with the reactance curve. It's not the impedance curve. And I say this because I have received a couple of emails from guys trying to do this method and have suggested it's not working, only to discover after talking to them that they're using the analyzer and they're looking at the impedance curve. That will not give you the results we're looking for. It's the real R that we want to look at. Okay, just a few summary comments. This is not, in my opinion, a trivial approach to tuning a parasitic array. First of all, expecting a Yagi to perform exactly as modeled in the field is somewhat naive. In other words, getting a plug and play result from a model. Element tapering, parasitic capacitance at the element mounts, boom, and element truss effects, etc. can all upset the real actual tuning. Especially for low band shortened Yagis like I've built, tuning can be very sensitive. Really and truly, field tuning a homebrew Yagi is almost certainly going to be required. The traditional tuning method, which I've used and I know many others have, has involved isolating the parasitic. In other words, detuning the driver in the field on the tower. And then using your antenna analyzer, you'll tune the parasitic to match the resonance point, which you've calculated in the model. In the model, you'll also isolate the driver by inserting, say, 1,000,000 ohms and then sweep the parasitic and determine its resonant point. Then you'll proceed to close the parasitic and tune the driver for a coax match. Then you'll do field tests to confirm the front to back using field strength tests, and then you're likely going to need to retune the parasitic as needed. Sometimes there's many iterations have been required. I mean, I've done this, and it's often quite a bit iterative, which equals a lot of tower time. This method also requires that you have an isolated or split element driver and parasitic. By tuning the parasitic by just observing the minimum R dip on the tower like I've described here and adjusting it for the correct frequency, relative to our desired 1-to-1 frequency, we can be confident that the Yagi is optimally tuned because all mechanical and electrical and driver interactions are accounted for because you're sweeping to find that minimum R dip, which is the resonant point of the parasitic, in the completed antenna with the driver and everything in circuit, as you will. Fine tuning can even be achieved by observing the SWR bandwidth. I may do another video on that, but it's, you can be confident on where you're tuned based on looking at the SWR bandwidth. Field testing really isn't required, and you can be confident of the tuning using this method, and I have done it. This method is very useful, especially when tuning a non-split parasitic or a grounded shunt-fed tower in, say, for example, a vertical array, like I've done.
Here are a couple examples of where I've used this very method for tuning my own homebrew Yagis in the field. Shown in the picture is my 80-40 meter Yagi, which I'm currently using. The 80 and 40 meter Yagis both share the same boom. Focused on the 80 meter Yagi, in fact, this is out of a paper I wrote, and on the left is the modeling, just like I had shown earlier here. On the bottom is the plot of the real resistance shown in blue, and you can see the dip in the minimum R. And you'll notice I've drawn a line here to tune this as a reflector, where you can see the maximum front to back and gain points. So I know that I wanted to tune my Yagi at this point relative to the dip. On the right is the actual analyzer sweep from the AIM analyzer. And you can see the real R shown in this orange line looks very similar, in fact almost identical, to my model. So I know, or I knew, I needed to tune the Yagi at this point with the bright red arrow. So basically on the tower, I just, whatever frequency I wanted to have the antenna tuned at, I made sure I adjusted the parasitic until it was at this point, and then proceeded to tune the driven element. In this case, I used an L network to match the driver. And I did the exact same thing with the 40 meter 2-element Yagi. I also have a 160 meter 2-element parasitic array, and in this case I'm using the shunt-fed tower. This is a US tower crank-up, and I put up 2 irrigation tubing parasitic array elements. They're spaced about 60 feet from the tower. And I did the same thing using this method to tune it. This was especially helpful since it's a grounded tower, right? So I can't isolate the driven element. On the left is the model. And again, on the bottom is shown the real resistance, and you can see that dip. And so I knew that I wanted, if I tuned the Yagi here on this solid red line, I'm at the maximum front to back or gain point. I knew where I needed to tune it. On the right is my analyzer sweep using the AIM analyzer. In this case, it's kind of cool because what I did is on the top faint yellow line, this was a sweep when I had the parasitics isolated. There is no parasitic, and you notice that this was the resistivity profile of the tower alone. As soon as I brought the parasitic into the circuit, you'll see the sudden dip in the real resistance. So I knew if I wanted to tune this array as a reflector model, I'd tune it here where I'm showing with my cursor, or down here if I wanted to tune it as a driver. In fact, in this case, I do that. I tune the parasitics, each of them, either as a director or a reflector to get 2 directions from one. By the way, if you're interested in these either of these antennas, I've written a couple of papers, one on the 80-40 meter Yagi as well as the 2-element parasitic array. I'll provide these links at the bottom of the video. 73 guys, have fun. I hope you learned something. If you want to build a Yagi, a 2-element, even just to experiment like I did in your basement, or just whip together an antenna. If you've got an analyzer, I think you'd be surprised following this methodology how easy it is to end up with a functioning 2-element antenna and have it tuned with confidence. See you later. Steve, V6WZ.